Hello everyone, I hope you're doing well, and in today's class we're going to continue from where we left in the previous class. And in the previous class we were able to do all the basic logics from the not, or, and we did a couple of levels. We did XOR, always on, second tick. The bigger XOR gate, we saw how we are able to chain OR gates to get slightly larger OR gate, and also AND gate. And we are going to see how significant it's going to be in using these signals to represent data. We also saw an XNOR gate, and today we are going to see a binary racer. So according to Google, a binary racer is a fast-paced minigame achievement. Okay, yeah, it's in Turing game, Turing complete. But let's see what this level is all about. We're also going to see. Okay, let's just explore and see. Says this level is my favorite pastime. Converting decimal into binary under time pressure. Okay, so a binary number, as we have established, a binary number is a number that's either 0 or 1. That's a binary number. And we also know another number system called a decimal. This is what we are able to use, like from 0 to 9. Yeah, from 0 to 9, that's a decimal number system. And every number that you know is made up of this. Like 1,000 is still made up of 0 to 9, but then it's 1, 0, 0, 0, and 1,900,000 also made up of the 0 to 9. So that's a decimal number system. I think a decimal number. Okay, looking at what a decimal number system is. A decimal number system, according to Google, is the decimal number system is a base 10 standard method for representing number that uses 10 digits, that is 0 through 9, and relies on positional placement values, and employs a decimal point. Okay, and a binary is just similar to this, but then it's based on base 2. That means you only have 2 options. In binary, in base 10, but you have 10 options, like 0 to 9. And we also have binary, we have 2 options, that is 0 and 1, and we can construct everything like 0 is 0 in binary, 1 is 1, or if we use 2 digits, it's 0, 1, 2 is 1, 0, and 3 is 1, 1. And since we have exhausted the digits, we can now have an extra digit, whereby now we have the next number, which is 4, as 1, then 0, 0, and so on. So that's a binary number system. And so we are going to kind of try to convert a decimal number. A decimal number is just the normal numbers that we use to a binary, but then under pressure. So let's go. So we are supposed to toggle the bits in this level panel so that they add up to the decimal number in the question. You must beat level 3 to pass. So click here to turn on timerless accessibility mode. I don't know what that means, but let's do it. Okay, start the race. What is the binary number 1? It's this. Submit. 2 is this. 3 is the 2 and 1. So this is an 8-bit kind of input. So by toggling this, we're able to get an output to represent a number we need. So submit. 13 is to be 8, 4, and 1. You add them up, you get 13. Submit. We are under time pressure, so I think we should do it a bit faster. 4 and 2, we get 6. 11 is 8 and 4. No. And 2 and 1. That's 11. 12 is this and this. 1 is 1. 14 is 8, 12, 2. 8, 4, 2. 0 is 0. Just like that. Wrong answer. Okay. Five is 4 and 1. 2, 4, 3, 15, 8, 4, 2, 1, 3, 2, 5, 30, 16, 8, 4, 2, 0, 0. 7 is 4, 2, 1. 6 is 4, 2. 10 is 8, 2. 6 is 4, 2. 14 is 8, 4, 2. 18 is that and 2. 47 should be 32. So okay, made a mistake. This is past that. So 8, 44, 45, 46, and 47. 7 is 4, 2, 1. We've had this some other time. 57 is 32 and 16 and 8 should be there, then 1. 11 is 8 and 2, 1. 32 is 32. 45 is 32, then should be 8, 4, and 1. 5 is 4 and 1. 45 still 32, 8, 4, 1. Yeah, I don't know why it's not there too much. Let me just try and end it. Okay. Good job, you've reached level 5. Okay. Continue. So recap. Hopefully you noticed. 1. There is exactly one way to write each number in binary. Exactly one way to write each number in binary. The value of each digit is always double the previous digit. So as you can see, we have 1, double of 1, 2, double of 2. It's like 1 times 2 is 2, 2 times 2, 4, 4 times 2, 8, 8 times 2, 16, 32, 64, and 28, and so on. And this is just an 8-bit representation of numbers. I think it is able to represent numbers from 0 to 254, 55, if I'm not wrong. And I also forgot to mention, we also have other kinds of number system. We have a hexadecimal number of system that is base 16. That means that a hexadecimal has numbers from 0 to 9, same as decimal, then A to F. So ending up to be 16. This representation of numbers it's more human readable, but yeah, it's just a bit human readable. We also have an octal number system, which is a base 8. Yes. And I think it also has ranges from 0 to 8 for some reason. But computers only understand binary, which is 0 to 1, which is what we're trying to represent with this. And all the other kinds of representations are what we're able to convert binary representation from, so that the information is a bit understandable for us. Like an application for the hex code that we're going to really see is it's used in representing memory. Like you can see some 0x, things like that. And also colors, for those who have been working with colors, we can see that some colors are like FF, C0, 11, or something like that. So that's a representation of a color, but using the hex, which is a bit readable than having the raw binary that will be just a long string of 1 and 0. But underlying this representation is converted to binary, which is the only language the computer understands. And that was a binary eraser. Our next one is the level is double trouble, and let's see what the level is all about. It says, because we are so technologically advanced, we have machines fold our socks. Unfortunately, the circuit that detects the sock pair broke on the machine. Okay. This level has 4 inputs. Okay, so right now we started with just a line with 1 input and an output. Right now we went to, I don't think we did 3. So now we are at 4 inputs, and these input signals are called bits. And these bits are able to form 8 of these bits are able to form a byte. And I guess 4 of these bits, they're able to form, I think, a word. And yeah, and bytes makes kilobytes, and kilobytes will be able to make megabytes. Of course, we all know about MBs. We also have megabytes, MBs making gigabytes. This is the amount of data. And we also have, from gigabytes, we have terabytes, petabytes, and so on. But right now we're just at word, which is 4 bytes. So it says this level has 4 inputs. Output green, output on when 2 or more of them are on. Okay, so if 2 of these inputs are on is when we, okay, so we need to know if at least 1 is on. So in order to know that, we can use an AND gate. An AND gate is able to tell us if these 2 inputs are they are on. So if either of these is on, we get an on. And if we want to get an extra, to check this again, and now this or this, no, I think it should be on, or get. If either of this so if 1, that's a problem according to what we read, because it says that this level has 4 inputs. Output on when 2 or more of them are on. So, but right now it's just 1. So we kind of want and the hint was, don't overthink this level, but so if 2 of them, still we get an on. But the problem is that if one of the inputs, just 1, we cannot have one input as on. So I don't know if we're supposed to check every bit. But let's see what we can do about it. An XOR, it checks if the inputs are different and fires a 1. Okay. And an AND gate, which is this, outputs a 0 if both of the inputs are 1. If both the inputs are 1, it outputs a 0. An OR gate outputs a 1 when both inputs are 0, otherwise 0. And an XNOR, which is it's not even here. It checks if the inputs are the same, and if so, outputs a 1. So even if we have our last input as on, we're supposed to get an off. So, and if we get, oh, okay, that's the top one. I think this should be an exclusive NOR, if I'm not wrong. Because, okay, let's see. Because if the first input, this should be an AND gate. Okay, so if the first input is on, we get an on. So we are eliminating the first because we don't have two inputs. And if we do get a second one, so this one should be able to contribute to this. Let's see. Because this is 2, that means the condition should be met. And if we take the lower 2, the condition is met, which is okay, because they are on different paths, this path and this path. So okay. Okay, so we want to take our first input and huh. And if the second one is on, it becomes on, and also there's the second two of them, which is the bottom two, which is this. And this. And again we AND them. But then we also need another combination whereby we have our first one and our second one, second one, and our next one, which is oh no, this should not work because we had an XOR checks if the inputs are different, and if so, it fires a 1. Okay, let's try using an XOR for some reason. So an XOR checks if the inputs are the same and inputs are 1. So if they are different. Oh, okay, we're checking if these two are different. If they are both the same, the outputs are 0. Okay, so this gives us a hint on top of here, and we can use another XOR. And we can also tell if this input is on or off. So they can't be both on. If they are both on, it becomes off. And then probably just AND. No, not AND. Or this. That means if we have 1 over here and 2, this should be successful, but it's not. So I'm really not sure how to deal with this level. If we try testing, if the first one, yeah, we don't get the correct answer. Again, the level log says that this level has 4 inputs and outputs. When 2 or more of them output are green, which is true. When 2 or more of them are on, are green. Okay. When 2 or more. So, when 2 or more. This is just 1. The only thing that can tell us if okay, we can pick an AND gate and tell us if this is on. If this is on, it's just 1. But if we have another one, if 2 are on, it's when it goes on, so that's true. But then we also have other combinations, so I can probably pick another AND gate and tell us if the first one still and the third one so if the first one is on and the third one is not on, we don't get, because it's just 1. And if we light the second one, we at least get that. And if we also through the third one, we at least get these 2. And we can pick another AND and pick the first one still, and this was the third one, and now the final one input. And now we can get this. And how about we go to the second one? So for the second one, we can do the second combined with the first one. So the second one alone, it does not light up something. Combined with the first one, it lights up this. The second one combined with the third one, it doesn't light anything, so it means we need to get another AND gate and pick this up and also pick this up, and that means we get this. And the second one with the last one, we don't get anything on, and now we can probably pick just an AND gate and just use this and this. Hope it's not the same. Yeah, and we go to the third one as on. The third one as on, alone doesn't get us any output, and the third one with combination with the first one, we get an output, which is this. Combination with the second one, oh, okay, we get an output, which is this. Combination with the third one, which is itself, that means it's just one input, so we don't get that. And combination with the last one, now we need another AND gate. Now we can extend. Now so after the third one and the last one, now we can test the last one. So the last one and the last one, that means just this output, we don't get anything, which is okay, which means it's just one input as on. And if it's the last one with the first one, we get an output. The last one with just the second one, we get an output. Last one, just the third one, we also get an output. And if we combine either of them, we still get an output. We still get outputs, and that's okay. And then we can OR all this, which are 6. There are 6, 1, 2, 3, 4, 6. So instead of using these 2, we can use an OR gate with 3 inputs, another OR gate with 3 inputs, and finally just an 2 level. So yeah, this level was a bit hard, but we were able, I think we are able to solve it finally without probably overthinking it. And now we can bring our output here and now test every level. And on the first one, let's test our first tick. Everything is okay. Second one, everything is okay because it's just one. Just one, still no output. 2, we get an output, and so on. And we are able to complete that by creating this circuit. And as per now, we don't know what we're going to do with such kind of circuits, but we should be able to see that in the coming classes. And our next class is odd number of signals. Okay. It says using a maximum of 3 components, output true only when the odd numbers of inputs are they are green. True. That means that we have 4 inputs. So if, as we know, odd numbers is a number, an odd number is a number that's not divisible by 2. Like an odd number, when divided by 2, I guess we get a remainder. So if we have 3 and divide it by 2, we get we get 1. we get a remainder of 1 because 2 is able to go into 3 just one time and with just one remainder. And since we have a remainder, that means that this number is an odd number, is not divisible by 2. That means it's not even. And so we need to be able to detect. So if we have just this, that means that okay, let me so if just one input is selected, that's an even number. If we need to identify odd numbers, if 2, that's even. If 3 or 3, that's an odd number. If 4, even. So that means just one that is even. That means that we want to identify just okay, so according to this, I think 1 should be an odd number. Yeah, an odd number. So that means we need to identify 1 and having 3. 2 is here and 3 is yeah, it's just 1 and 3. If we just have 1, that's an odd number, and if we have 3, that's also an odd number. Those are the two conditions that we're checking. 3 inputs as green and 1 input as green. That should be easy because we have an AND gate which can check 3 of any inputs that we want. We can do this, do this, do this. We can also use another AND gate to check the next 3, which be first one, second one, and the last one. So we have checked the first one, second one, third one, first one, second one, last one. As first one, second, third, first, second, last. Now we light this, and third, we light up this, and we are done with that. And we can check. Can use another AND gate to see if we can check second one. We can't do first one because first one we have done all the combinations. So we can do second one, third one, fourth, which we can pick up the signal from here here, and second one, and I don't think there is another combination for the second one, because second one, yeah, I think it's done, because second one, third one, fourth one, if we change to second one, first one, second one, first one, it was already covered. It's already covered by these two. And if we take third one, fourth, first, second, fourth, first, third. Ooh, okay, that's not taken. First one. Oh, third one. First, okay. Then last one. First one. Second one. It's already covered still, so I'm not sure if we have left any other combination. So this covers where we have three of the outputs as on, but if we have 4 of them as on, three. Zero, zero, zero. Zero, zero, zero. So from this, we can see that but the problem is that if we get a fourth one, that's an issue. Oh, and we do have a limit. I didn't really see that. We can only spend 3 components. So this is wrong, because we already have 4 AND gates. So I think we should just scrap our thinking and start over again. Odd numbers of signals. So we have 4-bit inputs, which are this. That means the combinations we have is 0, 0, 0, 0. Our next one is 0, 0, 0 1, then 0 0 1 0, then 0 0 1 1, then 0 1 0 0, then 0 1 0 1, then 0 1, which is same as looking at this truth table. 0 1 0 0, 0 1 0 1, then the next one is 0 1 1 0, then 0 1 1 1. That I know from binary is that's binary representation of number 7. And our next one is 1 0 0 0. Next is 1 0 0 1, then 1 0 1 0, then 1 0 1 1, then 1 1 0 0, then 1 1 0 1, then 1 1 1 0, then finally 1 1 1 1. That's everything. And this is from 0 to 0 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. As you can see, this is 0 and this is 15. And we want to identify odd numbers of signals. Let's see, 1 1 0 1, 1 1 0 1 is 1 1. Looking for 1 1 0 1. That's odd. Whoa. And it's actually corresponding to the decimal numbers, because from 0 to 15 we have 1 as an odd number. We also have 0 1 0 0 0 1 0 0. That's 4. But they're talking about an odd number of signals. So if signal is 0, let me see. Zero one 0 1. Let me see. 0 1 0 1 0 1 0 1. For here we just have 2 of the signals as on, so the signal is even. This was the number 5. I wanted to see if it corresponds to the decimal one. So we only want to know if we want to find out the odd numbers of signals. Okay, so when something is a bit easier, a bit harder or challenging, what I'd do is use, again from the previous class, is called the sum of products. So, and just from the sum of products, try to construct a solution out of that. And let's see how, if we're able to do that. So for the sum of products, we should be able to look at these signals to satisfy the columns whereby our output is 1. So over here we can look at this and say that if this is A, B naught, so this is 1, 2, 3, 4, 5, 6, 7, 8. That's a problem because we have a limit of the number of components we're able to use. So that means that our hint is somewhere over here, and we just can't see it right now. Okay, and as we can see, it says that an XNOR outputs a green when inputs are the same. So if inputs are the same, output a green. If the inputs are the same, we output a green. If both of them are green, are red, output a green. If both of them are green, output a green. But an XOR, when outputs are green, are true when they are different. Oh, I think I get it. An odd number. Okay, so if the first input and the second one, and the next one and the final one, so if just one, we output a green, which means this is an odd number. When they're even, we get this just off because it's even too. And the same as this one. If just one, we get the output we desire. If both of them, we don't get the output we desire. And again, if this and this, that means we also need to exclude. That means it's even, so we need to compare also the two inputs. And if we have 3, then it's a good one. Yeah, I get it. But it took a bit of time. So because 3, 2 is even. Two is even, but if we add another one, this becomes odd. Then over here, since they are different, becomes true. And also over here, since they are the same, off. Since they are different, true. So without a doubt, this is the solution. Yeah, it took a bit of time, but we got there. So that's how we construct a way to detect odd number of signals. Just two XOR gates and another one to conjoin them. And this should be the last level for today's class. Says in our education system, we traditionally teach by tricking students into doing the wrong things and then teasing them. That's brutal. Make a circuit where the input of a component depends on its own input. Okay. I'm not sure it benefits the students, but teachers love it. Create a circular dependency. Circular dependency is whereby you one thing depends on one thing depends on itself, right? For those who have done a bit of programming, we have seen this circular dependency, whereby you are importing something, but then it's like you're kind of importing yourself. Yeah. It says create a circular dependency. This is a circuit where the input of a component relies on its own output. In a circular dependency situation, it's not possible to determine the output of a component because you would first need to determine the input. It's like the chicken or the egg problem. So which really came first? Is it the chicken or the egg? So this is an issue. This is an error. It's ambiguous. Because you would first need to determine the input, which relies on the output, and so on. Hence, the circular. This state is normally not allowed in other levels, but in this level, the goal is to create it so you understand what it is before going forward. Make a circuit where the input of a component depends on its own, so we can just have an OR gate and just have the yep, that is a circular dependency. Check. Create a circular dependency involving at least two components. So we can have another let's use an XOR gate. At least two. Says or at least two. Can have it doesn't matter what it is, but we just want to have this is not, I don't think this is a circular dependency what I'm creating. Okay, it is. Check. Yeah, and we have fortunately completed this level. So this, as we can see, is an error, and we should avoid creating such kind of circuits. And I believe that's the end of our class for today, and I'll see you in the next class. Bye.